Hello friends, welcome to this lecture. So, if you recall in previous few lectures we have defined the term stability of a solution of a non-linear system or a system, and we have discussed certain example to illustrate the concept of stability. And in previous lecture we have say find out method to find out the stability of the linear system. This is the x dash equal to Ax, and we have seen that the stability of any solution is equivalent to stability of 0 solution, and stability of 0 solution can be determined in complete manner provide with the help of the eigenvalues of the coefficient matrix A. So, we have discussed the following theorem, that if all the eigenvalues of A, say lambda 1 to lambda n, have negative real part, then 0 solution is going to be stable solution. In fact, it is more than a stable solution, it is asymptotically stable solution, and that part we have discussed in previous lecture. And in the second part we have seen that if at least one of these eigenvalues have positive real part, then 0 solution is going to be unstable solution, and hence all the solution of x dash equal to Ax is going to be an unstable solution. And the C part, if one of the if all the solutions all the eigenvalues have non-positive real part and corresponding to eigenvalues with 0 real part, if Am is equal to Gm, algebraic multiplicity is equal to geometric multiplicity, then all the solutions are stable solution. And if algebraic multiplicity of any eigenvalue with 0 real part is strictly greater than geometric multiplicity corresponding to that eigenvalue, then any solution of x dash equal to Ax is going to be unstable solution. So, we have discussed the part 1 in previous class previous lecture. Now, we continue with the second part, that here we are assuming that at least one of the eigenvalues of A has a positive real part. So, let us consider here, let lambda V be an eigenpair of the matrix A. That means that lambda is an eigenvalue of A and V be the corresponding eigenvector of A. So, let us consider one eigenpair of matrix A and also assume that lambda has positive real part, right. So, it means that here we are taking only one say eigenvalue which has positive real part, then we can simply find out the solution as psi t equal to c e to power lambda t into V is a solution of x of x dash equal to Ax for any say constant c. And now we may have two different cases. One case is that lambda is purely real or lambda is a complex eigenvalue. So, if lambda is real, then we can show that V is also real, and hence we can write down the norm of psi t is equal to modulus of c e to power lambda t into norm of V here. Now, the modulus of e to power lambda t is nothing but e to power lambda t itself, and here we can see that as t is tending to infinity, then psi t is tending to infinity. So, it means that it may happen that initially your psi of t naught is less than delta, but this but we have already shown here that psi of t is tending to infinity as t tending to say infinity. It means that I cannot find out any epsilon greater than 0 such that norm of psi t is less than epsilon for any delta such that norm of psi t naught is less than delta. So, it means that whatever epsilon you will choose, since this norm of t is an increasing function of t, we can always find out some time t such that norm of psi t is not less than this epsilon. So, it means that your psi t is not a stable solution. Now, this is the case corresponding to a lambda real. Now, consider the case when lambda is a complex eigenvalue. So, corresponding to a complex eigenvalue, we have a complex eigenvector, let us say V1 plus I V2, and then we write down the solution like e to power alpha plus I beta t into V1 plus I V2. This implies that e to power alpha t cos beta t plus I sin beta t, and we are writing V1 plus I V2. Now when you simplify and we can take out the real and imaginary part, I can write down e to power alpha t V1 cos beta t minus V2 sin beta t plus I times V1 sin beta t plus V2 cos beta t. So this is your real part. So real solution I can write it e to power alpha t and V1 cos of beta t minus V2 sin of beta t. So this is also a solution of x dash equal to Ax, and the imaginary part is e to power alpha t and V1 sin beta t plus V2 cos of beta t. So out of this complex solution we have got two real valued solution of x dash equal to Ax. So let us take one real value solution, let us call it psi 1 t. Psi 1 t is c e to power alpha t V1 cos beta t minus V2 sin beta t. Now look at the so this is a real valued solution of x dash. Now we can look at the norm of this, and if you look at the norm of this, then it is what, and this is bounded by say norm of V1 plus V2, but this quantity this, so it is less than or equal to e to power alpha t modulus of c, and this quantity is bounded by, you can say norm of V1 plus norm of V2. So we can simply say that so here we can calculate the norm of psi 1 t, which is given as norm of c e to power alpha t V1 cos beta t minus V2 sin beta t, and this I can write it modulus of c e to power alpha t and norm of V1 cos beta t minus V2 sin beta t. And here if we simply say that if c and either of one of V1 and V2 are non-zero, then corresponding to any constant I can find out a t large enough such that this quantity is bigger than the given constant k. So it means that I can always find you take any epsilon here greater than 0, I can find out a t suitably large such that psi 1 t, norm of psi 1 t is bigger than this epsilon. So it means that you even though your psi 1 t naught is less than your delta naught for any delta, but I can always find out a suitable large t such that norm of psi 1 t is bigger than epsilon. So it means that this quantity cannot be made small for all t greater than equal to t naught, and hence we can say that your 0 solution is unstable, and hence every solution of x dash equal to Ax is unstable. So this simply says that if at least one eigenvalues with the positive real part exist, then all the solutions of x dash equal to Ax is going to be unstable solution. So here now we try to discuss the part C. So here we are assuming that some of the all the eigenvalues, we are assuming two things. First, that all the eigenvalues are having non-positive real part. Second thing is that some of the eigenvalues are having 0 real part, right. So it means that not all the eigenvalues have negative real part. So in part A, where we have assumed that all the eigenvalues are negative real part, and then we have shown this thing that norm of psi t is less than or equal to nk e to power minus alpha t norm of psi 0, and this we have shown in the first part. But here I am assuming that all the eigenvalues are having negative real part, and hence we can choose your minus alpha such that minus alpha is bigger than minus alpha 1, where minus alpha is 1 is the largest largest negative real part of eigenvalues. But here, since some of the eigenvalues are having say 0 real part, so I cannot choose minus alpha which is say less than 0. So here I have to use some other say method. So now let us assume that A has some eigenvalues, say lambda 1 to say lambda r, which are having say negative real part, and lambda 1 r plus 1 to say lambda n, they are having say 0 real part, right. So, we already know that the corresponding to lambda 1 to lambda r, if we consider find out the solution say psi 1 t to say norm of psi r t, we know that this is less than or equal to say k e to power minus alpha t norm of psi of 0. So, corresponding to these we know that each one is satisfying this condition, but corresponding to this we need to know whether they will satisfy this or not. So, if you consider lambda r plus 1 to lambda n, and here we are assuming that am is equal to gm, means algebraic multiplicity is equal to geometric multiplicity. It means that they are having the eigenvectors and there is no generalized eigenvector exists. So, it means that corresponding to lambda r plus 1 to lambda n, we are having say Vr plus 1 to say Vn as corresponding eigenvectors, and we can find out the solution say psi r plus 1 t as e to power lambda r plus 1 t Vr plus 1 and so on. So, it means that corresponding to this I can simply write the norm of psi r plus 1 t is less than or equal to, I can take the same constant k here as or some other constant k1 e to power say simply this is simply this has 0 real part. So, lambda r plus 1 t is basically the complex value. So, norm of modulus of e to power lambda r plus 1 t is basically bounded by 1, and we can simply say that it is norm of Vr plus 1. And if we include these two, we can say that psi r plus 1 is less than or equal to, we can denote this quantity as kr plus 1. Similarly, this I can do for all r plus 1 to n, and we can choose. So, it means that up to say 1 to r it is bounded by this, and r plus 1 to n it is bounded by kr plus 1, kr plus 2 up to kn. So, now we can choose the maximum. So, we can choose k as maximum of this this earlier, let me choose some k tilde. K tilde is maximum of k, kr plus 1 to kn, right. So, this implies for this k tilde we can simply say that psi of t, norm of psi of t, which is nothing but maximum of norm of psi I t, I is from 1 to n, then this is less than or equal to k, k times norm of psi 0, right, because up to r plus up to 1 to r it is bounded by k e to power minus alpha t norm of psi 0. Now, this quantity is less than 1. So, I can say that norm of psi 1 to psi r t it is less than k norm of psi of 0, and for r plus 1 to n it is bounded by kr plus 1, where kr plus 1 is nothing but k1 times norm of Vr plus 1, right. So, we can say since these are constant eigenvectors, so I can find out the norm of Vr plus 1, and we include this with k1 to write kr plus 1. So, it means up to kr plus 1 to kn we have some other values, and then choose k tilde as maximum of k comma kr plus 1 to kn. So, we can say that norm of psi t, which is nothing but maximum of norm of psi I t, is now bounded by k times norm of psi 0, which is which we are writing it here. So, if it is bounded by k times norm of psi 0, I can simply say that it is bounded by n times k times norm of psi of 0, where k gives you the max sorry, here it is k tilde. So, here we can simply say that every quantity is less than k times norm of psi 0. So, I can simply say that norm of psi t is less than n k tilde norm of psi naught for every solution psi t of x dash equal to Ax. So, now we have shown that there exists a constant k tilde says the norm of psi t is less than or equal to n k tilde norm of psi naught. Now, we want to show that this quantity is less than epsilon. So, make this quantity less than epsilon. So, this implies that norm of psi 0 less than epsilon by n k tilde, and we can choose this quantity as delta, right. So, here we can simply say that this k tilde is a positive quantity. So, epsilon by nk tilde is defined and we can take this quantity as delta. So, it means that whenever norm of psi naught is less than delta, this implies that norm of psi t is less than epsilon, and hence hence we can say that 0 solution is an stable solution, and hence we can say that every solution of x dash equal to Ax is also a stable solution. Okay. Now, let us so here we have assumed that Am is equal to Gm. So, that so here we have used this condition, so that all the eigenvalues say corresponding to r plus 1 to n, they are all say simple eigenvectors, means constant eigenvectors. There is no existence of generalized eigenvector exist, and hence we can show that norm of psi t is less than or equal to nk tilde norm of psi 0. Now, if we assume that A has fewer than kj linearly independent eigenvector, where this kj is the algebraic multiplicity of the eigenvalue lambda j. So, it means that here we may have solution psi t of the form psi t equal to c e to the power I sigma j t u plus t times a minus I sigma j I into v. So, here it may be something more, but I am writing it like this, that the simplest form of the solution may be like this: psi t equal to c e to the power I sigma j t u plus t times a minus I sigma j I v, where u is the eigenvector and v is the generalized eigenvector. Right. So, here we simply say we want to show that this solution is going to be an unstable solution. For that we can simply say that since V is a solution of what? V is a solution for this A minus lambda j I, V is non-zero, and A minus lambda j I V square is equal to 0. Now, this I can write it as A minus lambda j I into A minus lambda j I operating on V equal to 0. So, I can say that this quantity A minus lambda j I V is a solution of A minus lambda j I equal to 0. So, it means that this I can consider this, that we already know that it has only one one linearly independent eigenvector. So, it means that A minus lambda j I v is a multiple of eigenvector u. So, I can write this as c e to the power say I sigma j t u plus some constant times, let me use some other constant, let us say that k1 t u, and that is all. So, we may have, so what we have done here, that if algebraic multiplicity is less than is strictly greater than geometric multiplicity, then there is a solution of the form like this, that psi t equal to c e to the power I sigma j t u plus t times a minus I sigma j I v, and where v is a generalized eigenvector and u is a eigenvector, and we know that by definition v is a solution of a minus lambda j I whole square v equal to 0, and this I can rewrite as a minus lambda j I into a minus lambda j I v into 0. So, it means that this a minus lambda j I v is a constant multiple of constant multiple of the eigenvector u, right. So, it means that in place of a minus lambda j I v, I can write it k times k1 times this u, right. So, k1 times u, if we write it, then we have psi t can be written as c e to the power I sigma j plus u plus k1 t times this u. Now, I can take this u out and we simply say that we have psi t equal to c to the power I sigma j t, this is what this I can write it I plus k1 t and u here. Now, if we take the norm here, since u is a constant vector, norm of this e to the power I sigma j t is 1 and norm of c. So, it is modulus of c and norm of I plus k1 t and norm of u. Now, this is a constant value, this is a constant value, but this is a polynomial function of t. So, as t tending to infinity, the norm of psi t is also tending to infinity. So, it means that psi t is cannot be bounded by any some given any epsilon. So, you can say that for any given epsilon you can choose t large enough such that this quantity is bigger than that epsilon. So, it means that psi t is not a stable solution. So, here we simply say that 0 solution is not stable, and hence any solution of x dash equal to A x is not a stable solution. Now, here we have discussed one more definition which says that how we define asymptotically stable. A solution x equal to phi t of dx by dt equal to f t comma x t is asymptotically stable if it is stable, and if every solution psi t which start sufficiently close to phi t must approach phi t as t approaches infinity. Why we are discussing this definition? It says that you consider one solution phi t and it is a stable solution, first thing. Now, we want to show that this is say asymptotically stable. What do you mean by asymptotically stable? So, for that if you take any other solution psi t which initially very close to this, it means that norm of psi t naught minus psi t naught is less than delta. Now, this implies that norm of phi t minus psi t, now this will be tending to 0 as t tending to infinity. So, it means that if phi t has this kind of property, it satisfies the following two properties. First thing, that it is a stable solution. Second thing is that as t tending to infinity, norm of phi t minus psi t is tending to 0 for every psi t which is which start near to phi t naught. Then we call phi t is an asymptotic stable solution. Why we are considering here? If you remember, in case of x dash equal to A x, where A has all the eigenvalues with 0 negative real part, we have obtained this thing, that norm of psi t is less than or equal to n k e to the power minus alpha t norm of psi 0. Now, here if you take t tending to infinity, then this quantity is tending to 0. So, it means that norm of psi t is tending to 0 as t tending to infinity. So, it means that if all the eigenvalues of the coefficient matrix A have negative real part, then the 0 solution is asymptotically stable solution, and hence every solution of x dash equal to A x is asymptotically stable solution. Okay. So, that is what we have discussed here. Now, let us consider certain example based on this. So, first example is that determine whether each solution x t of differential equation x dash equal to A x, where A is given as minus 1 0 0, 0 minus 1 1, 0 minus 1 minus 1 is stable, asymptotically stable or unstable. So, here we want to see whether each solution is stable or otherwise. So, here as we have discussed in previous theorem, this whole thing can be determined if we know the eigenvalue of the coefficient matrix A. So, here the coefficient matrix A is given by this minus 1 0 0, 0 minus 1 1, 0 minus 1 minus 1. So, we first calculate the eigenvalues of the coefficient matrix, and it is coming out to be lambda equal to minus 1 and lambda equal to minus 1 plus minus I. So, this part I am leaving it to you, how to find out the eigenvalue of the coefficient matrix. So, if you look at carefully, then lambda 1 is equal to minus 1, lambda 2 equal to minus 1 plus I, and lambda 3 equal to minus 1 minus I. So, if you look at the the real part of each eigenvalues, it is minus 1 here, it is minus 1 here, and so it means that every eigenvalue have a real part which is strictly negative. So, it means that here we simply say that 0 solution is not only stable solution, but asymptotically stable solution, and hence we can say that every solution of the differential equation x dash equal to A x, where A is this matrix, then it has to be asymptotically stable. So, here I just want to point out one more thing, that if all the eigenvalues are strictly having strictly negative real part, then it is asymptotically stable. If all the eigenvalues are having non-positive real part and corresponding to 0 real part, if algebraic multiplicity is equal to geometric multiplicity, then solution is stable solution. In that case, we may not get the asymptotic stability, but all these solutions are stable solution. So, please recall, if eigenvalues are having non-positive real part and corresponding to 0 real part, if am is equal to gm, that is algebraic multiplicity is equal to geometric multiplicity, then every solution is a stable solution. And if at least one of the eigenvalues are having positive real part, then all the solutions are having are unstable solutions, right. So, that is what we have discussed from this theorem. Now, we have one more very important observation from this system, that stability of any solution x t of the non-homogeneous system dx by dt equal to ax plus f t is equivalent to the stability of the equilibrium solution x equal to 0 of the homogeneous equation x dash equal to x. So, that is very important observation, in the sense that even if we have any function f t non-homogeneous part, some force function, but we have no change in the stability behavior, that if this linear system is stable, then whatever force you want to apply on this system, it will remain a stable solution. And if dx by dt equal to ax is having unstable solution, then f t will not change any the stability thing. So, f t has no role in determining the stability behavior of dx by dt equal to ax plus f t. So, this is an autonomous system. So, autonomous system, stability of autonomous system is totally depending on the eigenvalues of the coefficient matrix. It will not depend on the say forcing function f t. So, let us just observe this result here. So, let us say that we want to have a solution, say phi t, and we want to check whether it is a stable solution or not. So, to check the stable solution of stability of this phi t, we consider another solution psi t of dx by dt equal to ax plus f t, and we want to check that for every epsilon greater than 0 there exists a delta greater than 0. Can we find out a delta greater than 0 such that norm of phi t minus psi t is less than epsilon whenever norm of phi t naught minus psi t naught is less than delta. So, that what we want to check. But here just observe this thing, that if phi t is a solution of dx by dt equal to ax plus f t and psi t is also a solution of this, then phi t minus psi t will be a solution of the linear part, that is dx by dt equal to ax. So, how we can simply say that phi dash t equal to a phi t plus f t and psi dash t equal to a psi t plus f t, then we can simply say that phi dash minus psi dash is equal to a phi minus psi, and that is all. So, it means that this phi t minus psi t is a solution of phi t minus psi t dash equal to a phi t minus psi t. So, phi t minus psi t is a solution of x dash equal to a of x, right. So, it means that the stability of phi t is equivalent to show that the 0 solution is a 0 solution of x dash equal to ax is stable, because I can look at here that call this the difference phi t minus psi t as say your x t, then I can simply say that this is nothing but this can be written as x t norm of x t is less than epsilon whenever norm of x of t naught is less than delta. So, if you look at where x t is what, where x t is a arbitrary solution of x dash equal to a of x. So, it means that this statement is equivalent to the statement that let x t be an arbitrary solution of x dash equal to a x, then for every epsilon greater than 0 we want to find out a delta such that norm of x t is less than epsilon whenever norm of x t naught is less than delta. So, it means that these two statements are equivalent. In fact, this also implies this, right, because if x t is an arbitrary solution and phi t is fixed, then I can say that phi t minus psi t, we can say that the difference phi t and x t, which is nothing but psi t, is an arbitrary solution. So, it means that these two are both ways. Okay, clear? Okay, so it means that the stability of phi t is equivalent to show that the 0 solution of x dash equal to a x is a stable solution. So, it means that stability of any solution of dx by dt equal to a x plus f t is equivalent to the stability of the 0 solution of the homogeneous equation x dash equal to a x. So, with this observation we end our lecture here, and we will continue our discussion in next lecture also. So, thank you very much for listening us. Thank you.